Welcome to Trustworthy AI Chronicles, where we explore the cutting edge of AI security, ethics, and innovation. My name is Dr. Ihsen Alouani from the Center for Secure Information Technologies at Queen's University Belfast. Join me to uncover the risks, share the breakthroughs, and spotlight the people shaping the future of trustworthy AI. Today, we are thrilled to be joined by Yanjing Li, Assistant Professor in the Computer Science Department at the University of Chicago. With a rich background in systems design and machine learning, Yanjing is at the forefront of research into robust and resilient computing systems tailored for AI. In this episode, we'll explore her insights on the challenges of designing secure and efficient AI systems and how her work bridges theory and practice to advance trustworthy AI.
So Li, Yanjing, I'm very glad to have you today. I hope your trip to Belfast was safe and smooth and you're having a good time so far.
Yeah, of course. Great to be here. And thank you for inviting me to this podcast. This is such an important topic that so many people are interested in. So I'm very happy to be part of this and discussing, many exciting things here.
Brilliant. Thank you very much. So Yanjing, I'll start with your career, have a chat about it, and then we'll dive a little bit deeper into the technicalities.
Sure.
So Yanjing, you have a PhD from Stanford, and then you worked at Intel Labs, and now you are assistant professor. So first of all, what initially sparked your interest, curiosity to the electrical engineering, computer science field? And then if you could walk us very briefly through your career and why did you go to industry and then back to academia?
Yeah, sure. So I've always been more interested sort of on the STEM field, like mathematics and sciences. And when I was a high school student, at that time, we don't have computer science in high school yet. But now I know like even elementary school students, they already studied computer science. But at the time, that was not the case. But I know that I enjoy mathematics and physics. But at the same time, those topics are also very hard. Like I think a lot of brain power, right? You need to spend a lot of that thinking about theoretical problems. But I also like some hands-on stuff. So I initially thought about applied physics. But then I think electrical engineering is pretty close to that, but even more applied. So that's why I went into CMU, their EC department. And then when I was taking different courses, I found like the systems side really intrigued me a lot. So that's how I continued, looking more into hardware and just those systems topic more. And I've been doing that since that time. And I guess my PhD is like everybody else's after I got to Stanford, very hardworking, many years in a PhD degree, also learned a lot, did a lot of exciting work. And I know that I like the academic environment, very vibrant and, students, right, interaction with them. So that has been my career goal all along. And also my family, like a lot of my family members, they are teachers and so on. So that might have something to do with that as well. But my advisor, Professor Subhasish Mitra at Stanford, I think he also has a similar career trajectory where he went to industry first and then went back to academia. And I think the thought there was that it was good to get some industry perspectives. And I interned with Intel a lot, actually, as a PhD student. And there were already, some projects that I started with. So at the time when it was almost about time for me to graduate, it just makes sense to, continue a little bit longer and then also gain some industry experience. And then I came back.
Brilliant. So now that you've seen both sides, both academia and industry, what would you comment on what's best thing that you enjoyed on both sides, and what are those different perspectives on the more or less the same topics?
Yeah.
Say systems, engineering, reliability, and so on. Probably different priorities from business and from academia. What are your insights on this.
Yeah, definitely. I mean, I think the difference between research in industry and academia is definitely different because in a business environment, it's all about business value. So I think your research would more or less tie to, what a company needs. I think from what I was doing at the time, it's not difficult to find some match between my interests and a company's bigger interest, although like we will not be able to have the freedom to look at things that are too, far, right? And too, I guess, impractical in a sense, like if you think about it that way. But still, like I think there's a lot of interesting problems. So I ended up liking that quite a bit, and the way that you think about things. And we also had a lot of programs interacting with academia as well, a lot of like university collaborations. So I feel like if I stay in industry, I could do more or less, the same thing with slightly different, of course, focus, right, on the exact topic that I'm working on, but I'll still be able to write papers, go to conferences, collaborate with university, collaborators, and so on. For our current job as, professors, I think the responsibility is research, but a bigger responsibility is to train PhD students and other students, right, who could eventually become the next generation researchers. And I think that is a very big part of our job and one that I enjoy very much. So I think for me, other than the topics themselves, I think that is a big difference. And I do enjoy the academic environment, interacting with students.
Yeah, I guess the perspective also from impact is different, while probably people in industry might say, oh, I see my ideas in products maybe a couple of years down the line, while in academia, that's probably not necessarily immediate, but it is on the long run.
Yeah, it's also possible. So I feel like wherever you are, you could do the things that you like. It's just that the way that you pursue things is a little bit differently. Yeah. So wherever you are will be good. Yeah.
Absolutely. Brilliant. Thank you very much. So now let's get a little bit into the technical part. So, and that also the reason why I wanted to have a chat about this with you is that you come from systems and hardware before being focused on machine learning per se.
Yeah.
And that's a very interesting perspective to have. So can you please, first of all, explain what are the unique challenges that machine learning presents for system design, particularly if you could elaborate from a robustness perspective?
Yeah, so I would say that machine learning is interesting for, computer architecture systems I would say in two ways. I think in one way, it actually makes the problem so simple because like if you're thinking about some other, CPU programs, the program structure could be very complex. And we know CPU, if they delve into the architecture, very complex with a lot of, microarchitectural features, right? But for machine learning, a lot of it is just matrix multiplication, accumulation, right? That's the only thing that we need to optimize. So in a way, our problem becomes much more focused. And from a hardware, architecture perspective, there are still, of course, ways we can, add in smart features and tricks to optimize everything. But in a way, the problem has been simplified, I feel like, because there's only this one thing that we need to worry about. But on the other hand, the scale of the problem is also very big. I think that the model itself is complex, right? Requires a lot of data. So a lot of the problem is maybe not so much on the compute side, but how does it interact with the memory system, with, everything else, right? Because how do we deal with all of that and provide this whole, optimization procedure for the entire workload? I think that is more of a fundamental question from a system design and architecture design perspective. And then the robustness dimension that you just mentioned is basically my home research area. So I feel very, like the need to really emphasize on that. Because when we are thinking about robustness, firstly, there's many different perspectives. I think you yourself is a security expert, so you are thinking about it from a security, privacy perspective. And my background is a little bit more on the reliability side. So But my problem is the following. I talk to people about reliability problems. I think people understand that from a traditional sense. But in machine learning, I think a lot of people would think about machine learning workloads as very tolerant already, right, to errors and noises and everything. So it tends to be overlooked a little bit when we're talking about reliability impacting the robustness of the workload. So there has been a lot of work that has been done for showing that that's not the case, but a lot of the study have been done on more memory type of problems. And I think at the time that we started this work, not a lot of people are looking at the logic, like processing engine, and if something goes wrong there, how would it affect the workload? So it has been a very big research focus in my group, and I'm happy to discuss, some of the outcomes and why we should care about hardware failures for machine learning, and it is a very big problem.
Absolutely.
Yeah.
I think that, again, that's a very interesting perspective, because people might think of AI as a concept, as a model, as something that's there. But at the end of the day, it is code running on hardware.
Yeah.
And anything could go wrong, not only from model understanding perspective, but also from a hardware perspective.
Yes.
And exactly your research is, if the hardware fails, what could happen? What could go wrong?
Yes.
And in order to have trustworthy systems, now trustworthy AI implemented on trustworthy hardware, and so on, we need to understand what could go wrong.
Exactly. Yeah. And there's not a lot of understanding on that. Even though, I think we are, very familiar with talking about adding noises to, to a model and so on. But the problem is, if there's a piece of hardware that went wrong, right? We don't know what it could. It may be more than just a noise. It could create actually a lot more disturbances to the execution of the workload and eventually lead to something very serious. There has been more work done on more inference type of workloads. So I think the most classical approach comes from a paper back in the 2017, and they show that with some transient errors in the memory, right? And if you're, let's say, driving a self-driving car or something like that, and you have a classification system, right? If there's some sort of like a stop sign or some like critical traffic signals, or if there's like a truck coming towards you, and with just like a transient model, the truck could become like a bird or something. So originally, supposedly, you should like stop the car, but then if it's just a bird, then you would just drive through, right? So that would become a very big security problem, or safety problems that's like life critical. So it's so important to consider those kind of effects. And I think later on, we actually have more studies. Some of them come from my group, some of them come from others. But looking at failures in the logic, not just in memory, and it could have similar effects as well.
No, that's interesting. You're taking the example of intelligent transportation systems. And there was obviously a whole line of work on adversarial attacks in which there is a manipulation of the input that leads machine learning models to fail.
Yeah.
Now you're talking about something else. The input is fine, and luminosities, everything is okay, and it is not a problem in the camera, it is not an attacker, it is some glitch, something goes wrong in the hardware, and suddenly it no longer recognizes and does what it has.
Exactly. And no malicious event here, right? So, and you cannot predict, because these things comes almost in a random manner, not predictable. So it's very difficult to take any preemptive actions.
Yeah. So from this perspective, one might say, okay, look, you're talking about wherever critical applications, but this has been around for a while, and people looked at the reliability, for example, from your perspective of those systems, and there are standards and so on and so forth. Why the AI opens the problem again, as if we're starting over and looking at those problems because it is going to be running AI?
Yeah, so there's some interesting things here. So for one, I think machine learning workload, we talked a little bit about this before, is very different from a traditional program. And then, so it comes with new hardware, right? Actually, like I think GPUs definitely is very big. And then if we're talking about intelligent transportation systems, then I think accelerators is also now like a big player in that area. So there's some definitely new architectures that we have to, take into account, and also understanding specifically for machine learning how it affects the workload. In traditional programs, it's almost easier in the sense that you have a set of outputs and you have one correct answer. And you're either correct or you're wrong. It's a very clean, one or nothing kind of approach, right? But in machine learning, things are stochastic and statistical to begin with. So most of the time, a hardware failure is not, or any other errors or noises, is not going to create too much of a problem, I would say. But when you are so unfortunately hitting a case where the hardware failure just happens at the wrong time, at the wrong place, and then a much bigger problem would occur, like the example that we talked about earlier. And I think the challenge is to figure out, first of all, what is okay and what is not okay, and how much we can tolerate, right? With a lot of confidence to say, yeah, no, we don't need to worry about these cases at all. And also, how do we figure out how we can deal with the ones, right, which are actually quite rare, that could create these big problems.
Yeah, that's interesting. So this problem, especially for critical applications, there are, for example, verification the tools and approaches that have been used before in classical, I would say, algorithms.
Yeah.
Now, with AI, it is not that obvious. You do not just say, I can formally verify an AI model for this application.
I think some people tried actually to do that, but I think the scale they're looking at maybe like a 2-layer, fully connected layer kind of. But I do feel that, if we can leverage from some formal methods into the approach, that would just give us so much confidence, right, in how much robustness we can guarantee in our application. And then I would say there's also another separate line of research, very classical fault-tolerant computing type of approaches, where they just add in redundancy all over the place in systems. So those approaches would, the main problem, of course, is cost.
Yeah.
If we have any constraints in power, area, or things like that, then it's very difficult to deploy those techniques.
Absolutely. So you're talking about power, and a part of trustworthy AI, potentially, the umbrella could include sustainability as well. Yes. We're having more and more very heavy models that are consuming lots of power.
Yeah.
So how do you see the road forward from this perspective?
Yeah, so firstly, I think so far we're only talking about inference. We haven't even touched upon training, right? So I think training is another consideration where I think maybe previously, like when we're thinking about robustness and when we're thinking about security, privacy issues, it's mainly an inference time kind of concern. Your model is all good. It's trained very well, right? And then it got deployed in real life. And then when we're running those models to perform inference, all sorts of things like hardware failures. Also, we call those silent error corruption sometimes. That's a bigger term right now, a buzzword right now. And security issues, that happens at inference time.
Yeah.
But actually in training time, there's another set of problems, right? And hardware failures, silent error corruptions actually could be, very critical in that area as well. And I think there's also security challenges. I've seen some papers. I think you'll know more about this than me, but those we all need to consider. And of course, training, from a more traditional, system optimization perspective, it's costing so much energy, right? Using so much resources, especially some of those really large models. So there's a constant need and desire to cut down those costs. And the sustainability angle that you mentioned would also fit in there very well. So, I mean, those are all the important problems that we need to consider.
Yeah. So a part of your work on training specifically, and I think that's one of the main novelties of your work, is that you looked at the problem, what could go wrong, not at inference time, while training a model, hardware fails.
Yeah.
Can you please elaborate on this and the concept of SDC, silent data corruption?
Yeah.
What does it mean? Why it is important aspect, especially for industry?
Yeah, it's very important. Actually, it was the story was that when we started this work, we actually first look at inference, just like everybody else. But as I mentioned, not a lot of work are looking at the logic part, right? I think a lot of people are looking at the memory part, but not the logic. So we started our study on just examining how hardware failures that occur in the logic, and they can be transient, they can be permanent. Transient means that the logic would just come, they may, the failure may come for just one cycle and then they would go away and the circuit is operating correctly again, versus a permanent, which just means that this problem will show up over and over again. But both of them could cause problems to the training workload, actually, or the inference workload. So we started inference, and then we have the framework already there that's validated and accurate and quick and everything. So we did a lot of studies on inference, and then we just thought, since we have this framework, it's just easy to throw in a training workload there to see, what we find. And I think at the time, like my students and I, we talked about this, and we're just like, we can add this as, an additional workload, and then we can add that to the paper and whatnot. But we really did not expect to see much of a problem there. Because if you're thinking about the training procedure, it's iterative and it's an optimization problem. So it's constantly adjusting its weight, right? Based on this objective, this loss value. Mm-hmm. So it's hard to think about how, if you have a transient hardware failure, that you may perturb maybe some values in some training iterations, but then the training procedure should be able to just correct it automatically. So we really did not expect to find anything, but to our surprise, very quickly, actually, this is maybe, my time perspective is a little off now because it's been, a year, more than a year, but maybe it's like a week or two, my students were running these experiments, and then he told me that, some of these things just completely did not converge. We spent such a long time, and we don't know what's going on. So we spent a lot of time debugging because we were just afraid that there's something wrong with our framework, which make me really nervous at the time. But after we looked at it very closely, it actually is just that it's even transient, it's not even permanent. Mm-hmm. But then hardware failure only lasts for one cycle, and it flips a bit in one of the flip-flops in the hardware, and then it completely went away, nothing was there anymore. But then the training procedure did not recover, basically, and the training curve looks completely weird, not like how you would expect. So that basically motivated us to explore more. And then later on, we even found more cases where there's different outcomes. There's the training curves looks very different, and but the conclusion was that, even just one single bit flip that happens in one cycle could corrupt the entire training process.
Wow, interesting.
Yeah.
So you mentioned you're a little bit anxious about having a bug in the code. I guess this is because you were running in a simulation environment that you guys implemented yourself in your team. But can you tell us if you had any tests in real life? Have you had any engagement with industry about this problem?
Yeah, so we did that, right? I told you that story. It's only part of the story. But then also around that time, there is a keynote that actually Google presented in one of the workshops that was happening at the time. And then they talked about, I think, bugs from hell. And then it turns out it's hardware failures that are affecting the training workloads. So Google did not disclose any of the details, of course, but they did tell us, and through our interactions also, I think we heard stories about how they train their network on their TPUs, and then all sorts of mysterious things comes up. Mm-hmm. And they don't know what that was at the time. They try a lot of very ad hoc approaches, debugging their software, spending a lot of time on software first, actually, going nowhere. And then they started to, I think they changed some voltage settings or something like that in their TPUs, and all of a sudden things start working again. And they I think there's still no good understanding why that's happening, but we know that it's a hardware problem and we need to look at it more closely. So that's why, like, later on, we had this collaboration with Google that explored this problem in more details.
Interesting. So I guess you verified your simulation findings in their system.
Yeah. So we did a bunch of simulations ourselves, and then my student went to Google and experienced some of the same, scenarios that we observe in our simulations in real systems as well.
Very interesting.
Yeah.
A part also of your work is some theory behind machine learning robustness. Could you point out to some theoretical gaps or knowledge gaps or challenges in designing reliable, robust systems for machine learning application, be it in training or in inference?
Yeah, in training and inference, I think the problem is, of course, the algorithms are, different, I think. But the mathematics, right, I think we sort of understand. I think so exactly, how a neural network performs, either in training and inference, I think that's well understood. I think maybe people don't understand why they work so well, but in terms of how it works, I think people understand it pretty well. I think that the challenge for designing robust systems for those workloads is that maybe one big thing is that we don't understand what exactly can go wrong in a hardware level, and it's very difficult to model. So traditionally, of course, people have certain models for all kinds of hardware failures. In manufacturing testing, for example, you have the very classical like stuck cat or transition. But do they really represent the error scenarios, the hardware failure scenarios well enough? I think nobody knows that. It's just an abstraction of what could go wrong, right? If you have a like open or something circuit open or something, you can model it some way. But is that the only way the hardware can go wrong, right? The answer is actually no. Like now we actually know that it's no, because it definitely, like some of the testing methods that we developed for manufacturing testing, they actually do not cover all of the manufacturing defects that can happen, let alone other failure mechanisms that would only manifest in the field. For example, aging problems or dynamic variation problems, which are happening because of, for example, voltage variations, temperature variations that are affected by a lot of different factors. It's just very difficult to model a very complex circuit environment interacting with a complex software workload running on top of that, and put everything, together and come up with a model to say, under what scenario this would affect the circuits in this way, and so this kind of behavior will show up, right? That is actually a very difficult thing to do. So for all of our studies, we rely on a fault model to tell us what we should target when we're thinking about how to design a system. But if that fundamental fault model is not well understood, then anything that we put on top of that is just limited, right? In the same way.
Absolutely.
So I think the biggest challenge is to, have a better understanding about that so we can protect our circuits better. But at the same time, that's more on a more fundamental, theoretical understanding side. From a practical perspective, I think we need to protect our systems no matter how much we understand about what's going on there. We may never be able to exactly answer that question, right? So I think, one of the biggest trends that I'm predicting that we'll be seeing in our systems in the future will be smarter and more proactive features, reliability and robustness features that's running alongside the system to help us screen out this kind of problems so we can react real time.
So you're thinking more of the necessity of some sort of self-monitoring systems?
Self-monitoring systems, yeah.
Very interesting.
For all kinds of threats. It doesn't have to be just for reliability, but I think for security, right? If you recognize, something very malicious that might be going on, we can do something about it. Yeah.
So the fascinating part of your work, as I see it from a security perspective, is that, let's say, an application of AI for health, for example, is a very critical, sensitive domain. So when I push the story, oh, look, this could go wrong if you suppose this threat model and this attacker and this access, blah, 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 it is sometimes people would say, yeah, I will just protect my data, or I will isolate my system, etc., etc., and it should be okay. Now, what you are saying is more or less the same risks that I am looking into. You're saying this could happen because of something in the hardware, and hardware can fail.
Yeah, exactly. I think a lot of the software, security work, I'm no expert, but they assume that the hardware is perfect, right? And then, of course, hardware security is a different community, but the other community, they would assume the hardware is perfect. But a lot of cases not, and then it's where some of the security assumptions could be violated.
Yeah. So the more we have advances in AI and scalability of problems it can solve, how do you envision the use of AI helping systems design? And is there any robustness, trustworthiness perspective on this trend?
Yeah, it is a very, very active research topic. I think it's using machine learning to solve a system problem that has been going on actually for a while already. I think initially, for example, in a CAD community, would be more on maybe design space some examples, right? At least would be some sort of exploration, like placement tools, right? How do you find a more optimized, routing methods or something like that? It's in a way, it's sort of a space search kind of problem. So machine learning, makes sense that it could work there. But now I think people are even taking that one step further and looking into how can we use, for example, generative language models to help with designing circuits, right? For example, is it possible that we tell, some sort of AI model to say, I want a circuit that can do this. And then the model would just spit out like the RTL or an actual circuit that can actually achieve that. That's a very active, research topic. But I think even in that step, there's a lot of interesting questions to explore. So I don't think that robustness is on anybody's active research agenda right now. But when we see the approaches, actually, we see more advances and more progress in that, I think then we shouldn't think about robustness as an afterthought, right? So I think at that time, it would definitely become more important. But I would say, it's important to start thinking about that now while we are coming up with new methods to utilize AI technology for system design. We should actually think about them together and not think about this after we have something, right? But so this would be a topic that I'm very interested in exploring.
Yeah, so let me zoom out a little bit and ask you about your opinion on, so there is this, people argue that this disruptive novelties that are happening in the AI field might be a threat to even to existential threat to humanity, like some of the thinkers and researchers even and academics might think more or less relatively. And some would, like Yann LeCun, for example, saying, this is just regular progress in whatever field that we already have. Do you have any thoughts on this debate?
I think everybody can have their own opinion. My opinion is that I think AI could replace a lot of tasks that we have today, especially those that are very well defined and very structured. Of course, all of the work that we're doing here, right, enabling robustness, reliability, I think all of that would be very important if we do want to completely replace what we're doing now with AI. But also, I think that the flip side is that human could make errors too. So who knows? Maybe it's good to have a collaborative relationship between what AI can help us do, and then we human, maybe we can double check or use our senses, right, when we make use of the result and, those kind of things. So I do think that for a lot of things, AI could replace those kind of tasks. I think it's not happening now. I think you probably have some answer now, but when I use AI tools, I can only speak from my experience, is that they help me a lot, but I don't feel like I can completely trust what they what they provide to me. So I always need to double check. So that's why I don't think that it's completely replacing everything yet. And on the more, if it involves any, creative, kind of more innovative thinking, I don't think the AI can replace human for that. Because I think our brain is still very mysterious. We don't know how it works. Even we want to build something like that, I think we're very far away from that.
Yeah, at least that's probably true, at least for a big range, let's say, of tasks. It might potentially replace some of the tasks.
Yeah.
But it also opens potentially more opportunities in other dimensions.
Yes.
Yes. So, if I might ask you again, from your perspective, what is the next big question that you're hoping to tackle in your research?
Yeah. So as I mentioned, I think my background comes from more from reliability, hardware failures, and things like that. But I think it has a very close connection with other very interesting and also very hot topics today. I think one dimension is security. So you and I talked about, rollhammer effects and things like that. So that is a very prominent example of how a reliability issue somehow is got leveraged and by an attacker, and that becomes even a bigger security problem, even more so than a reliability problem. That's just one example. There are others there. So that's an area where I think of course, it's very big, but I'm also personally very interested in. And then another dimension is actually linked to sustainability as well, because all of these techniques, affects carbon footprint. It affects how we design the systems. So it's also a big focus now. So one example of looking at sustainability and reliability is this aging effect, because all circuits age. So basically, their performance would degrade. For example, over time, when you run your computer at day one, it's not the same as if you run it 2-3 years later, because the circuit is actually slower at the time. So if we have a method that can, for example, make the lifetime longer, that's a way of a direct link to sustainability, for example. So that is, those are interesting dimensions to explore. And then a more, I would say this problem has been around in the architecture hardware community for a long time, is that everybody is thinking about, okay, we are very close to the limit of silicon scaling. So how far can we push it, right? After 1 nanometer, what comes after that? Maybe 0.5 nanometer? I don't know, right? But
famous Moore's law.
Yeah, the famous law, Moore's law. So what comes after that? So there's a lot of emerging technologies that people are investigating. And then another dimension comes from, AI is becoming, so prominent everywhere. And we talked about, the operation from a compute perspective is really simple, right? Compared to, we don't need very complex, computation engines. So actually, a lot of technologies could be very interesting and already inherently can perform these operations, resistive memories, optical technologies. Very interested. I'm also very interested in those dimensions, basically envisioning after silicon, right? What is beyond that? What else can we turn into a computer? It could be using other devices. It might be using, I think some research are looking into even organic materials, but what does the next generation of computers look like? So I think that's a big problem.
Very exciting.
Yeah. And it wants to, and I think I would very much like to be the one who's coming up with the next generation, new computing paradigm.
I'm very confident you will have some breakthroughs. Well, thank you very much for your time, Yanjing. It was really very fruitful and very enjoyable. It's a very short trip to Belfast. Thank you very much for coming over, and thank you for agreeing to record this episode with me. Thank you very much.
Thank you.